Hello, everybody.
Hi,
My name's Paul,
and I'm Jamie.
and we're here on our first trial of a podcast for the open source satellite. We're some space people, as in we're not going to space, but we are in the space industry, and we're also software engineers, embedded software engineers. So we write software for the embedded systems on board spacecraft. And this is a video about some of the things we've learned about some of the latest processor technologies that are available and how they can be utilized for the space environment. So it's a very niche, nuanced sort of video, but it's kind of one of those things that, I wish I had learned this 5 years ago, some little key little snippets of information that you might find useful if you're embarking on the use of some new processor technology on spacecraft. We've been sort of, going on a bit of a journey with the open source satellite. We've been trying to develop a new spacecraft platform for the future of the space industry and trying to sort of bring about a bit of a step change in the space industry by making this new design open source. Woo, that'd be cool. And as part of that, we thought, right, we need to develop some of the main components on the spacecraft. And one of the main things on the spacecraft is its brain, yeah? And we needed to, develop that. It's quite a key component, really, the main computer inside the spacecraft platform. And so we had a look around. We had a collaborator called Mauricio Di Carvalho. I love the name. And he did a sort of a look-see around all of the different processor technologies that kind of fitted the bill. We came up with some requirements. It must have a bit of memory. It must have this kind of amount of performance. And our requirements were all based around the idea that we could try and make this onboard computer do as much as possible. So, all the things that you need to make the spacecraft stay in space. So it must perform attitude control. It must be able to communicate with the ground using like CCS type protocols or something equivalent. It must have a file system. It must be able to store data. It must be able to schedule activities on the spacecraft. All of these different things. We wanted to try and get as much as we could into one thing, so that we've got quite an integrated platform that consumes a lower amount of power because it has not big distributed systems. And so we had a look around and we found some processors, and we thought, right, okay, we are part of the new space industry, but we're going to try and do things in a sort of quite a good quality way, and we're going to try and radiation test these things because, by radiation testing them, we'll have confidence that they'll work well in space. So we took 3 processors and we tested them, and that's where this guy comes in, actually.
Yeah, actually, because this radiation testing was actually one of the first things I did as my career change into this industry, becoming a software developer. And this was a collaborative project between the University of Surrey and KISPE, it was the company we work for, and yeah, so Maurizio, he chose the processors, and I wrote the code that would go on these processor boards. And the University of Surrey have what they call the reef facility, and they have this chamber in the reef facility where you can put in electronics and stuff like this, and then it will blast it with radiation, and you can get some results out of that. So I wrote the code that went on these processors. They went in the chamber, and then whilst getting irradiated, the code and the chip and the processors would test the memory on the chips and all the different peripherals and stuff like that. And we would get a constant stream of data that we would use to analyze the health of the unit under test. So that's what I did, and it went quite well, actually. So we chose 3 different processors that we tested. We had an STM32 chip from ST Microelectronics. We had 2 SAM chips from Atmel that is now microchip. We had the SAM V71 and we had a SAM A5D3 chip. And the performance of this, from our findings, is that actually across the board, the flash tended to fail first. And you can see the results of these tests on our website at opensourcesatellite.org if you wish to see them. So...
Yeah, absolutely. And what we did find is that all three of these chips, when we put them in the radiation chamber, they all seem to survive up to around 70 kilorats of total ionizing dose, which is a fair bit of radiation, given that these are commercial components. They started to degrade at that point. Some of them started to fail, and like Jamie said, the weakest bit seemed to be the flash memory, didn't it? Out of those three, during the development process, we kind of got to know these things a bit, got to know the development environments, got to know how they work and all that kind of stuff. And we had our favorites. So, if I had to do a kind of top three processors of the three that we chose, then coming out at number 3 would be the SAM A5D3. The reason this comes out at number 3 is partly because it's a bit of an older chip. It wasn't so good. It didn't have so many bits inside it. Basically, it didn't have any embedded flash. So usually these microcontrollers are a little chip, a little square, a bit like that. Can be like that. Probably can be like that as well. But anyway, they're little squares, and inside them is all the gumph. As in. Most of them have like embedded flash memory, embedded SRAM, cache memory, lots of peripherals, not profiteroles, peripherals, and but this SAM A5D3 didn't have flash memory, so unlike the other two, so you can't run code directly from the processor. You have to have some external memory, and you have to load it with some program and stuff. So that was a bit unattractive, not very integrated design.
From what I remember, that was quite difficult to get going in the first place.
Yeah, totally. It was tricky. It was tricky to get going. These chips, the SAM A5 processor family and A5, A8, A9, these things are designed to be running an operating system like Linux or something like that. Trying to get them to run bare metal, trying to run FreeRTOS with them, and embedded type environments is not so easy. It wasn't a pleasant experience from what I remember. There were some lovely people on the internet who had done an open source kind of embedded bare metal repos for SAM A5D3. Really good people, but it just wasn't as easy to engage with as some of the other two chips that we chose. The other two, we had the SAM V71. That comes out at number 2, the SAM V71. And the reason it came out as number 2 is basically just because, this chip and the other one, the the STM32, were similar. STM32 probably about double the performance. It was faster. The STM32 was lower power in our experience.
They both had ARM M7 chips.
Yep, ARM M7 cores. Yep. But I would say the SAM V71 fell down a bit in terms of usability. Trying to write the code with it, try to use it. It was harder work, I would say, than the STM32. SAM V71 came with a development environment that's based on Atmel. It's called Atmel Studio. It's based on Visual Studio, and now it's been bought by Microchip. They're trying to sort of move everybody away from Atmel Studio to MP Lab.
Yeah.
So there's kind of like all these different environments, and it's all a bit okay. Which one do I use? Not really sure. It just wasn't as easy to get going with. The STM32 was really nice to get going with. It's got a development environment called STM Cube, and it's based on Eclipse, and there's lots of nice tools to sort of, you select your chip and then you say, I want you to write a load of code to put an operating system on it and to enable all of these peripherals and all this kind of stuff. And it's all really easy and nice. And then you can say, look, here's a picture of my processor, and I want that pin over there to be a a clock output, and I want that one to do that, and I want to do, it's all very visual, very nice. And then you just hit a button, and loads of code gets spat out, and you just go, my job here is done. But I would say, yes, it does feel very nice to hit these buttons and for this code to be created for you, and you feel like, oh no, I have a minor crisis. There's no need for us software engineers anymore. But I would say that the code that it produces, I'm not saying it's low quality. I'm just saying it's quite complicated. It's quite verbose, quite difficult to maintain, quite difficult to use beyond just getting it to work. If you want to do something very nuanced with it, like maybe, I don't know, use interrupts rather than polling or something like that, you can run into sort of trouble. It can be difficult. So we've taken the step to actually write our own stuff. I'm sorry, STM. But the SAM V71 and the STM32, they both do this kind of code generation shenanigans. I would say the STM32 is just kind of better at it.
Yeah, even with the wizard, you have a picture of the whole clock domain, and you can say auto calculate the clock, or I want a clock of this for this peripheral, and it will just calculate and do it all for you, which is fantastic.
All very clever.
Yeah. We just ran into a few bugs at some points with some peripherals where things weren't working slightly, and we had to tweak things with the code. It's just the nature of the fact that you've got a wizard auto-generating code that would work on all the different families of chips with lots of different peripherals, all and supporting loads of different modes. So that's kind of understandable. And when you're writing code to go into space, you need stuff that's really testable, stuff that like you have full control over. So that's why we've been rewriting our own bits, basically, to replace it over time.
Yeah. So other things to note about these processors and things that we wish we'd known, going back to the SAM V71. So the SAM V71 is a commercial processor. It's used in cars quite a lot, engine management units, that sort of thing. And it's a good chip. It has different bits of circuitry around that ARM M7 core, which are the peripherals. So the SAM V71, I think, has 2 CAN controllers. It's got several UARTs. It's got SPI, I2C, probably 3 or 4 each. It's got loads of different sort of peripheral bits and pieces that you can use to connect to different bits and pieces. But what I would say is that, and that's great. But then they've got these other chips in the same family. They have the SAM RT71, which is rad tolerant. Sounds great, because when you're in space, there are problems with radiation. And that's why we had to radiation test our commercial processors. This chip has some kind of cousins in the same family that are rad tolerant, designed rad tolerant from the ground up. Yeah, sounds amazing. But there are some things you should know. If you develop your code for a SAM V71, the commercial variant, when you move to the rad tolerant variant, all of a sudden, all the peripherals are now different. And then the same is true when you go to the RH71, the rad hard one. They're just different. You can have your code running on a SAM RT71, and you think, haha, you feel smug, I'm going to put that onto my rad hard processor, and it sounds great. But then you realize that your driver for your UART, your RS-422 peripheral, is not working on your rad hard version, and the reason is because they changed the peripheral, and it doesn't really, don't know why. Maybe there's a clever reason. Maybe there's people cleverer than me. I'm sure there are people cleverer than me, in fact, actually. I'm very, very sure of that.
But it means when we've been running projects where we've been using this chip, we've used the SAM V71 to kind of start to develop the code, but the actual flight unit will be using the rad hard version. So we found out when we decided to port it over that all this stuff's quite different. Literally all the peripherals were quite different, or ones that look like they might be exactly the same. When you look a little bit closer at the datasheet, there were some stark differences that you had to account for. So it wasn't as easy as just take it from this one and stick it on this one.
Yeah, definitely. So that's worth knowing. And the STM32 family tends to be a little bit nicer from this perspective. They tend to use the same kind of peripherals across the entire family. So if you have a CAN driver that works on a SAM M3, it'll probably work on a STM H3 or whatever. It'll probably work on an STM H7 as well. Which is fantastic. But there are some downsides to the STM32 as well. And the major one that we've really come up against is the ECC. So, what is ECC? Like I said, radiation in space is a problem. So if you've got a satellite that's flying through space, it's going to get hit by high energy radiation from the sun. And the problem is that when it gets hit by the high energy radiation, ones turn to zeros and zeros turn to ones, and now your software doesn't know if it's what's going on, because it can't cope, because the one was a zero and now it's a one and I don't know what's going on anymore, right? So that is difficult for the software to deal with. And what these manufacturers have done, because nowadays you even see these kind of effects on the ground. Woo, dear, that does not sound good. And there's cases, if you're interested, on elections where they've used computers to count them votes, where the voting's gone a bit skew-if, and the reason is because the computer that counted the votes has got hit by the sun's radiation and has caused a bit flip that gave someone a whole load more votes. Look it up on the internet, it's quite interesting if you like that kind of thing. But the ECC, so the error correction code, the ECC functionality on the STM32 processors, it has this stuff, and essentially what it is, if there is a bit flip in a bit of memory, let's say it's memory that big, so 8 bits, let's say if there's a bit flip somewhere in there, then it's got this functionality that when you read that out of the memory, it can correct it. So it has this other area with like a hash code in it, and there's some maths that happens between the two implemented in hardware, electronics, that as it reads out that memory, it actually performs a correction. Magic. Yeah, it sounds good. And it is good. And that's part of the reason why we chose this chip, right? But the problem is that you have to write code, and that code gets triggered when there is a bit flip. So your software can say, oh, great, I had a bit flip over there, and you can send a message or put that into memory or something, and then you can report that to the ground, and everybody goes, oh, look, that memory over there is going a bit wrong, that kind of thing. Very useful. But the problem is that this code that you write, you want to be able to test. So you want to trigger a bit flip. That is difficult to do. Now the SAM family, the microchip SAM stuff, they've figured this out, and they've got test modes in their thing that allows for this to sort of cope, So you can put it into test mode, you can try out stuff, and you can trigger your software. Fantastic. STM32 not so much, and we found it quite hard to test. There are several ECC memories in the STM32. The RAM, it's difficult to test that. Okay, so the way we devised to test it, get this right. So we found a way. It's not easy, but bear with me, all right? Stick with me. This is how we've done it, and this is what I wish I'd known. So interesting knowledge. Hopefully it's interesting for you. But if you, so as you power up a microprocessor or a RAM, an SRAM, the content of the SRAM is random. It's just going to be 1 zeros. Don't know what it's going to be. It's very exciting. You turn it on and it's 1 0 1 0, and then you turn it on again and it's 0 1 0 1. And those kind of fluctuations are based on temperature. They change with various bits and pieces. So if you turn on your processor, then basically the content of the memory, including the hash code, is random. Now, what usually happens is when you start writing your code, the very first thing you do in some bit of assembler in your code base is that the software writes a known pattern into this. It could be zeros, could be ones, could be, I don't know, some stuff, And by writing it into the memory, you actually update the hash table which goes alongside the memory. So you're sort of allowing the ECC to work properly. because you're saying, here's the memory and here's the equivalent hash. Now, if you just turn on your processor and the content is random, then as you read out data before you've initialized the memory, so you haven't initialized it, as you read out data, the hash code will be different to the memory. Yeah, so that triggers an error, which is great because it means you can test your ECC code. So that's the way we've devised how to do it. Maybe there's other ways. STM, microelectronics, if you're listening to this, please tell us how to do it. But there are downsides to it. The main downside is that it's not deterministic, you know. Then one time you'll turn on the processor and it will fail on address 3. The next time you turn it on, it will fail on address 37, you know. There's no rhyme or reason for when it's going to fail. So that becomes difficult to, you know, produce reproducible tests. So something to note. The other part of the memory that that we have to test is ECC on the flash memory. And that's more tricky to deal with, and we're devising a way to do that. And our thoughts are, right, what we'll do. Flash memory, that when you erase a flash memory, what actually happens is it sets all of the content of all the cells to 1, okay? 1, 1, 1, 1, 1. I've got a friend, actually, she finds it funny that I talk in binary, but, you know, she's in marketing. And if she ever sees this video, she'll be like, oh my goodness, you actually did a podcast where you spoke in binary? Who are you? Kind of thing. But anyway, so when you erase a flash memory, the content goes to 1, 1, 1, 1, right? That's all good. So it's a known content, right? Now, what usually you do is you'd write into that memory to make the bit pattern that you want, you know, storing an image, storing some ASCII string, whatever it is, you know. And so that changes the content of the memory. Now, flash memory has the capability to change, once erased to 1, 1, 1, you can change the content of the cells from 1 to 0, right? What you can't do without erasing it again is change from a 0 to a 1. Okay, so it can only go one way. So what you can do in order to test this ECC, if you put a pattern in there, like, I don't know, 0, 1, 0, 1, 0, 1, as you write the pattern, the hash code will change alongside it. Okay, so that's fine. So now the hash code matches the memory. But what you can also do is you could change some of the other bits that are currently 1 to a 0. Now, if you're clever about it, then the way that you do that, then the RAM, the actual memory, no longer matches the hash code, because the hash code is also stored in flash memory and it cannot transition from a 0 to a 1. So you end up in a situation where now the hash code does not match the memory, and next time you read that memory, ECC failure, and you can test your code. Woohoo! So that's what we wish we'd known when we first took on these processes. Hopefully this is useful to you. What other stuff have we learned about these processes, mate?
Well, there was some other problems with ECC that we found whilst actually figuring out how to test it in the first place. So I wrote some drivers that would, when an ECC error happens for the RAM, it would trigger an interrupt, and you'd be able to look at some registers to see there was a bit blip here and the value was this. Well, we have a fantastic collaborator called Kevin who was writing some tests to test these functions. So he figured out how to trigger an ECC error in the RAM. But what he was seeing in the debugger was when one was triggered, the contents of the registers that tells you where the error was and the value was saying some really crazy stuff, some stuff that doesn't make sense. So why was this? And he spent a lot of time trying to figure it out, until one day he decided to turn the cache off, and this fixed it. Wow. Why would it do that, you ask? Well, first, let me explain to you what cache is.
Cache.
So, cache memory. If you imagine you've got your chip and you've got your RAM that you're writing into with and reading from with all your data whilst you're executing your code. Well, there's an extra bit of memory that exists right next to the chip. So that, and the chip, when you've, and this is the cache memory. So when you enable the cache and the chip is writing in and out and using the RAM, it can decide, oh, I've used this bit quite often, so I'm going to move what exists here into the cache. So when I go to read that bit of memory, I'll actually go over to the cache instead, because the cache is actually much quicker and it's got a much faster connection to the chip. This is all fine and dandy when the chip is in control, because it makes sure that what's in the RAM and what's in the cache is synchronized. However, when you have a different bit of hardware that the chip's not aware of that changes some memory, for example, the ECC controller triggering an ECC error and writing some of that the ECC error data into those registers, where the chip might have actually cached that value in the cache. Well, the ECC peripheral has written some new data in the RAM. So what's happened now is what's in the RAM and what's in the cache are out of sync. So when you go to read those values and seeing it in the debugger, for example, it's just a load of rubbish. So a way we're thinking of, because we would like to have the cache on, because it speeds up the speed of the processor quite some bit. So what we're thinking of is the STM32 has a peripheral called Memory Management Unit. And this is a peripheral that you can use to point at a bit of memory and say, this bit of memory, I don't want you to cache stuff that's in here. So we're thinking if we write a driver for that, we can point that maybe at the registers for the ECC and then switch cache back on, and the cache should hopefully no longer affect that interaction. So that was one of the problems that we've solved by switching the cache off, but hopefully we can work around that in the future so we can switch it back on. However, there was another problem that Kevin was having. And even with this, with the cache off, he was getting good values the majority of the time, but sometimes some rubbish. And he figured out that actually after a while of trying, he decided to stuff off the debugger. Let's try old-fashioned print statements. When he did that, it worked. So sometimes when you're banging your head against the wall, wondering what a problem is, it might be the tool you're using to debug in the first place.
Yeah, totally, yeah. Yeah, annoying, that kind of problem, you know. You got these tools, these debuggers and stuff, and you think, oh, fantastic, I can rely upon those. And actually, sometimes you can't, which is a bit annoying, isn't it, really? And you waste a lot of time. But that's just the way of life, really.
Yeah. So talking about quick memory and cache, there's also some other fast memory we can use that's actually unique to the M7 core. Do you want to tell us a little bit about that?
Yeah, so it's a bit like a cache. It's called a tightly coupled memory, and there's two kinds. There's the I, or instruction TCM, useful for holding your code, and there's D TCM, or data tightly coupled memory. So basically, it's like a cache. It's just a slightly bigger and slightly slower than the normal cache. And the way it kind of works is that you generally sort of use it in a static way. So you sort of say, as you compile the code, you say, I want to put this in the tightly coupled memory. And it could be a bit of data, it could be a bit of code. So for example, if you got an interrupt service routine, you want it to run real fast, stick it in ITCM and it will run a lot faster than it would if you just leave it in the normal flash memory or RAM. So yeah, anything else to really?
Well, whilst we're on the whole topic of speed, as well as memory being quick, there are other ways that you can use to transfer data that's much quicker. And this is via something called DMA, Direct Memory Access. Now, this is a specific peripheral that we have on this STM32 chip, and it also exists on the Sanvi 71. And the way it works, as you can see here, is the direct memory access controller has a concept of streams. So these are like specific channels that you can put data on, and they can move data from a source to a destination. This could be from memory to another bit of memory, or from memory to a peripheral, or a peripheral into memory. So you can use this to move memory around, to move data around, or to transmit stuff from memory over a peripheral, or to receive stuff from a peripheral into memory. Much quicker than you would if you got the processor to do it, because this is a separate bit of hardware that you basically point at one place and at the other and hit go, and it will do it on its own in hardware.
Light speed.
Light speed. Really good stuff. However, it was quite a beast to get going. And the problems I had were the way that DMA interacts with certain peripherals can be very unique depending on the peripheral in question. The way I got it working with UART on reception, and that was interesting because you had to configure it a certain way in the UART and do it in a certain steps specifically for UART so it would work. And a colleague of mine has recently done it with SPI, which has a slightly different way of configuring and a slightly different steps you have to go through to get DMA working. He was doing transmission, I was doing reception. So the interesting way with reception via UART over DMA is that you get stuff in over your UART interface. It would then, the DMA controller would move it through the stream and then out the other end into a buffer. Now I configured this as a circular buffer, so it would fill all the way up, and then when it got to the end, it would loop around to the start again and continue. And there was an interrupt that went off when it was halfway full and full way full and completely full. So then the chip would then be prompted to come and start doing stuff with that data. So this is all things that actually, when it comes down to transmitting and receiving data, if you can offload that onto hardware, then the chip can go off and do some other better, nicer tasks that could be more higher priority, rather than just polling or just writing data into a transmit buffer in a big loop, for example. So that was really good stuff. It was hard to get working, but there was one problem I had, and this would be very, very useful information for someone who's trying to get DMA working. This relates to our earlier problem with cache. When I wrote this driver to receive data over UART by DMA, it was putting it into that buffer I spoke about. When I tried to read the data in that buffer, it was saying some random stuff. Now, you could probably guess what the problem was, but it took me a while to figure out.
Hang on. Can you guess?
Can you guess?
We have like some kind of like questions going on.
Yeah.
And caller number 3. No, the answer is not Australia.
No, it's not Africa either. So I switched the cache off, and it worked. So basically,
it was the cache.
It was the cache.
Yeah.
So what was happening again was the chip had some idea of what was in the buffer, which it would put into cache memory, and the DMA via hardware was spitting stuff into this buffer whereas it via hardware, and the processor doesn't have any clue about what's going on in hardware with that. So it was the cache and what was in the buffer were getting out of sync. So when you go to read, it was a load of rubbish. So switch the cache off, or like we said earlier, use your memory management unit to declare that buffer as not cacheable, and it will work.
Right. Well, what can we conclude? If in doubt, turn off the cache.
Yes, it solved a lot of problems for us.
Unless you need the cache, in which case leave it on and then solve the problem another way.
Yeah.
But I hope this has been useful to you.
Yeah.
If you are, in the very niche group of people worldwide who want to use ARM processors in space, there's probably how many people are there like that? How many people do you reckon?
No, not.
Couple of thousand?
Probably it's a very niche subject.
Yeah.
But it's some useful information, because if we can help someone not spend weeks and weeks banging their head against the wall on some very, very specific problems, then that's a win in my book.
Yeah.
So upon reflection, what have we spoken about?
Well, we talked about ARM processors in space, ARMs in space.
ARMs in space.
And we've talked about RAD testing. Our results are on our website. We talked about the processors that we like, the STM32, the ones that we like but not quite so much, which is the SAM family. Sorry, microchip. And then we talked about some nuances between these processors and the things we wish we'd known. I hope that you found this useful. We're going to go home now because it's Friday.
Oh,
which is great. And it's 5:15. It's nearly home time. So, have a great weekend, everybody. Unless you're watching this in a weekday, in which case...
probably likely.
Sorry. What else was there to say?
Well, yeah. Thanks for watching. Thanks for coming. And, thanks for enjoying ARMs in Space.
ARMs in Space. Bye-bye.
See ya.